we're going to jump to planar graphs. I don't know what section that is in the book, or the notes, I guess. But anyway, this is like a really fun topic. So we'll be spending a few weeks on this for sure. Okay, so planar graphs. All right, so what is a planar graph? Well, I'll write the definition in a second, but it's very simple. A graph is planar, so some graphs are planar, some are not, if you can draw it in the plane and avoid crossing edges. Very nice concept. In fact, we often have drawn our graphs with no crossing edges. You can't always do it. There are graphs for which you cannot do that, and there are graphs for which you can. That's the whole point of the planar graphs, is discussing when you can do one or the other. But that's what makes it planar, and the planar graphs are somehow nice to work with because you can draw them and they're not complicated, but you know, they're not all planar. Okay, so a graph, say G, is planar if we can draw it in the plane. Okay, I'm not going to say more than draw it in the plane, but that means the vertices are points in the plane, and you have lines between vertices make up edges. Not necessarily line segments. They could be, it may not be straight line segments. You can draw them however you want, but you can draw it on the plane and avoid edges crossing. Okay, and so what does that mean exactly? You know, some more formal definitions will say that any two edges only intersect in a vertex is rather what they mean. But I think crossing is pretty clear, right? Like here's an edge that's drawn like that, and here's another edge that's drawn like that. That's a crossing, right? This is a crossing. But when two edges meet in a vertex like that, I mean, that's not a crossing. Otherwise, this whole definition would be nonsense, right? There'd be nothing to do. So this is okay, right? That's not a crossing. Okay, so we want to avoid this situation here. And this graph here of these two edges is planar, despite the fact that I've drawn it with a crossing, because all we need here is there a way to do it? Can we do it? If we can draw it without a crossing, then it's planar. It doesn't mean every drawing is a planar drawing, but just is there some way to do it? Okay, so such a drawing is called a planar embedding or drawing of the graph G. Okay, so this is a distinction that's going to come up a couple of times. Is when we're talking about G and we're talking about a drawing of G, they're technically two different objects, right? G is a graph. It has its structure. It has its incidences between vertices and edges. And then there are infinitely many different drawings of G. And some of those drawings are planar embeddings, thus establishing that G is planar. And some are not necessarily planar embeddings. They could be drawn with crossings. Generally, when a graph can be drawn without a crossing, we will draw it without a crossing, but you know, not always, right? So like maybe look a simple example here. So like the complete graph on 4 vertices is planar, and that's a proof, right? That's K4 with planar. Actually, we're just going to use the shorthand PE. So we'll call this PE, a planar embedding. Right? Versus K4 drawn without one, right? So here's a K4, and it's drawn without a planar embedding, right? That's still the same graph, but it's not drawn in a way that's a planar embedding, so not a planar embedding. And this doesn't help us establish whether it's planar or not, okay? Maybe let me draw another K4 with a planar embedding just to emphasize something here. But we can modify this picture, right? And this is actually a helpful technique sometimes in actually doing this by hand. So we had this edge here, and then we had this edge here, and we didn't want them to cross, but this edge here I can redraw by just like going out this way here, right? This is a PE of K4. Looks very different from the one above, and it doesn't, not all the segments are straight, but that's fine, right? This still establishes there's a drawing and I have no crossing edges. Actually, it's pretty easy to see how I can transform this one into this one, right? If I take this vertex and kind of pull it into the middle in such a way that this segment here can become straight, then I can, you know, establish that picture there. So this is like handy, like if you've used like GeoGebra and drawing programs like that, when you take a vertex that's connected to an edge and drag the vertex, the edge will like go along with it. So this can actually be very helpful for like visualizing or figuring out what's going on with stuff. Is like, imagine that this is like rubber bands joined to you know, pegs on a board or something like that, and you can kind of like move the stuff around. Like think of it sort of mechanically. It can be handy, and you want to, you know, you want to untangle it. I don't want the rubber bands to cross here in order to establish whether it's planar or not. Okay. So the study of planar graphs, though, is in many ways like a subdiscipline of topology. Like we're drawing something in the plane, and actually this suggestion of rubber bands and moving things around sounds very, very topological. I'm going to gloss over most of the topological details, as many as we can. If you're interested, the Diestel book, the first section or two on planar graphs, establishes quite a lot of topology, and it's actually very, very interesting. It's just not the best use of our time in this class, because virtually all of the topology we'll use is always like obvious seeming. It isn't always easy to prove, but it's like, oh, that's clearly true, and you can get away with that fact. And the number one of those will be the Jordan curve theorem, which I'll state and explain real quick here, that we'll just use as an assumption. We're not going to prove it, but it's a well-known theorem. Okay, so the study of planar graphs requires, we often need the Jordan curve theorem. Okay, and the Jordan curve theorem is very simple. It says that a Jordan curve, whatever that is, I'll define it in a second, whenever drawn in the plane, splits the plane into two pieces: the inside of the curve and the outside of the curve. You've probably seen this one before. Okay, so what's a Jordan curve? Actually, Jordan curve is very simple. It's just a closed continuous line. What do we call this? Curve is the term, right? I can't even say curve, like it's not a graph theory thing. That doesn't intersect itself. So a continuous closed curve in plane. Oh, we should say non-intersecting. Non-intersecting. So it doesn't go back on itself. Curve in the plane splits plane into exactly two regions. The interior, we'll call it, and exterior. Okay. So like, you know, what's a Jordan curve? It's very simple. It's like just a curve like this, and it splits the plane into the interior and the exterior. Okay. And so we'll use this fact repeatedly, that if I draw a closed curve in the plane, there's an inside part and there's an outside part, and exactly inside, exactly outside. And everything is split into one of those two. Okay. And the theorem is that, yeah, that this is the theorem right here, that this special type of curve, not even that special, does this, right? And I don't want to dwell on it, but like you might even say, well, why is this a theorem? Like this is completely obvious that this is true. And those of you that have come across this, it's not that hard to prove, but it's actually not trivial. It's not instantaneous, right? This actually requires some thought in topology. I hope a number of you have seen this, but we'll be taking this as a fact, which is a pretty reasonable thing to do. One, it's true. Two, it's certainly intuitively obvious, right? And the truth, it's important that it be true for the things to be for planar graph, you know, theory to work out. But we won't have to refer to it back to it directly too many times. And again, we'll just use this intuitive fact that we can. Okay, so this is what always comes up when Jordan curve theorem is mentioned, that it's obvious, in quotes, but non-trivial. Okay, all right. So we'll use that, and a couple times when we actually invoke it, I'll try to emphasize when we are, maybe the first couple times. Okay, so as an example, we saw that the complete graph on 4 vertices was planar, because like this picture here already establishes it. Let's find some graphs that are not planar, because we've seen planar graphs throughout the class. Like often when I drew networks or connected graphs, I just chose an example that was planar, so it was nice. So what's not planar? Okay, so we'll call this a proposition. So K5 and K33 are not planar. Okay, so later we're going to learn a more general theorem that has something to do with these two graphs that characterizes whether a graph is planar or not. These are not the only two examples, but these are two graphs that are not planar. Okay. And we'll also learn more sophisticated tools for testing whether a graph is planar or not. For now, we're going to kind of do like a brute force proof here, okay, in some sense. Although you might wonder for a little bit, how do you do a brute force proof? Because as of now, how would you prove something's not planar? Well, the only way to prove it is to show that every single drawing fails to have a no crossing, right? So no matter how I draw it, I get a crossing. Well, that's obviously impossible, like directly. I can't make every drawing. There's infinitely many. So I need to think a little bit more generally here. And this is where, you know, topology is going to be in the back of our mind when we do this. We're going to do for K5 only. K33 is going to be an exercise. This isn't that hard either case here, but okay. So what do we know about K5? Well, it has 5 vertices, and every pair of vertices has an edge between them, okay? So if I draw 2 vertices in the plane for my K5, I know there's an edge between them. It might not be like that. It could, you know, it might have reason to go like crazy in order to reach there to avoid other things, right? And in fact, this of course makes, again, proving the theorem sort of a challenge because, well, wait a minute, like, you know, how do I know which way it looks? And how it looks depends on whether there's a crossing or not or whatever, okay? So let's let V1, V2, V3, V4, and V5 be the vertices of K5, okay? Fortunately, K5 is highly symmetric, so when we talk about what it looks like in the plane, it's relatively easy here, okay? Okay, so any 3 vertices of a K5 form a triangle. I mean, in the graph sense, they form a K3. And they'll form a triangle in the plane, but I say triangle in quotes. Again, it may not be a triangle with straight lines, but they're 3 vertices and they have the edges between them, okay? So the 3 vertices, V1, V2, V3, form a triangle in the plane. Okay, so yeah, all right. How are we actually doing this proof? This proof is my contradiction, okay? Let's suppose we have a planar embedding, okay? So suppose we have a planar embedding of G, all right? So, well, of K5. So say we've drawn K5 in the plane without crossings, and we're gonna get a crossing here, okay? So these 3 vertices form a triangle. What does that mean here? Well, so what do I actually mean here by triangle? I just mean that those 3 vertices, you know, they're joined this way in the graph. Like this is not part of the planar embedding. I don't know that it looks like this, but they form a Jordan curve, right? The 3 edges here will form a Jordan curve. So that's what I mean by a triangle. So a Jordan curve. So this like set of 3 vertices forms a Jordan curve. Okay, so here's V1, here's V2, here's V3. I don't know, I still have to basically draw something here, but the proof doesn't rely on this picture being drawn in any specific way. Say my Jordan curve looks something like that, okay? Again, it's not going to be important, but the 3 vertices definitely form a Jordan curve, right? Because all 3 are joined to each other, no matter how it's drawn, it's like this, okay? All right, now observe that vertex V4 either lives inside this curve or outside this curve. Now I'm using Jordan curve theorem, right? There's only an interior and an exterior. This curve splits the plane into interior, exterior. So any other vertex V4 is either on the interior or the exterior, okay? Is on interior of V1, V2, V3, or exterior of V1, V2, V3, okay? I mean, this is an abusive notation. I don't know, like the V1, V2, V3 represents the curve, but yeah, okay. Okay, so let's suppose V4 is on the interior of V1, V2, V3. The case that it's on the exterior is very similar, but I'm just gonna do interior for now, although maybe we can sketch exterior too, okay? All right, so then if it's on the interior of it, well, let's actually just continue it in the picture above, just so it's easier to understand. Then V4 is like somewhere here, right, if it's on the interior. Again, I want this proof to not depend on the picture, so let's try and keep in mind that this picture could look anyhow, but I still think it's illustrative here. Okay, now V4 is adjacent to V1, V2, and V3, right? So there's somehow curves between this guy and these other guys, and these curves are where do these curves live related to the triangle V1, V2, V3?
They live inside it.
Absolutely, Brad. Yeah, they're stuck inside the interior here because if they end up outside, then they crossed somehow, right? And again, that doesn't rely on the picture, right? That actually just relies on the Jordan curve theorem. Okay, so edges V1, V4, V1, oh sorry, V2, V4, and V3, V4, all on interior of V1, V2, V3. This is by, again, Jordan curve theorem. And this was Jordan curve theorem, okay? If V4 was on the exterior, then all those would be on the exterior, okay? And then actually the Jordan curve theorem tells us something else, is these three lines coming out of V4 and going to V1, V2, V3, they split the interior of V1, V2, V3 into three regions, okay? You have to just apply Jordan curve multiple times, but this splits V1, V2, V3 into three regions. Okay, so the inside gets split into three parts here. And we see that illustrated in the picture as well. Okay. And those three regions, of course, are V1, V3, V4, V1, V2, V4, V3, V2, V4, right? We can name them if we want. Okay, and then the last step is, I'm just gonna do case analysis. So the last step we're gonna do by pictures, but you could write all these out. The last step is that there's no place for V5 now, okay? Now, V5 can't be placed. Why? Let's look at the picture here, okay? So now the plane has been split up into four regions. I've got these three regions inside of V1, V2, V3, and don't forget the unbounded region out here, which we got in the initial application. So no matter where I draw V5, I have to get a crossing edge. That's evident by looking at the picture, so let's actually go through it. Say it's in this region here. Say that's V5. Well, V5 can join to V1, V2, and V4, that's fine, but it cannot join to V3 because V3 is on the exterior of V1, V2, V4, and V5 is on the interior of V1, V2, V4. So there's no way to draw an edge. That's the picture, but I also said the words, right? The words were, where does V5 live? It lives on the interior of one of these three, or the exterior of this one here. It's in one of four regions, each of which is bounded by a Jordan curve. And there's always a vertex, it's just case analysis, on the opposite side of that face, right? So V5's here, it can't get to V3 except by crossing an edge, but there's no crossing edge, right? That's impossible, okay? If it's here, then it can't reach V2. It has to go out, cross that one. If it's here, then it can't reach V1. And if it's out here, then it can't reach V4. It's got to cross one of these faces there, okay? Or it's got to cross the face V1, V2, V3 to get there, okay? So that's why, okay? So I'm not going to say more words than that, but, well, we can say V5 and some vertex from V1, V2, V3, V4 on opposite sides of a curve. Opposite interior versus exterior, okay? So that's like pretty simple there, and I hope you can see that the drawing wasn't important here. We could write out all the words here. In practice, though, when you draw pictures here, as long as you're general enough, it's okay to include them. It's certainly helpful to the reader to have pictures. Okay, K33 is similar. You take an embedding that's planar, you find some faces, it's a little bit different, some regions, and then once you've got that, you can argue that you have two vertices that are on opposite sides of a curve, and there's no way to cross that curve. Okay, all right, so now we need a couple definitions here. So let me give one here by example, rather than writing out the words here. I may not have even defined this in the notes here. So say we have a planar embedding of just some graph G, okay? So a few terms that we use here. They're faces of the planar embedding. Okay, and this is very illustrative because we have like an actual polyhedron here, which have faces, but it doesn't have to be a drawing of a polyhedron to do that. So the faces of the planar embedding are just all the regions given by Jordan curves here, okay? So this is a face inside of here, this is a face inside of here, this is a face inside of here, and there's one more face outside of here, this unbounded face, Okay, right? The exterior region is also a face. If you think of this for a second as a polyhedron, right? The polyhedron has these three faces and the bottom, which you can think of like if you draw this in the plane. You don't have to know about polyhedra. It's just closely related to this thing here. Okay, so this is the unbounded face. Okay, so there's kind of a special face, although in practice it has no difference from the other faces in terms of the mathematics and the graph theory. But it's often when we draw it, it's often useful to talk about, mention the unbounded face. And these are bounded faces there. Okay. So yeah, when you have a planar embedding, your graph now has a new property, the number of faces in the drawing, right? This drawing has 1, 2, 3, 4 faces. Okay. The number of faces we'll talk about next time. Here's another planar embedding here of some other graph, right? And this says this is a face, and this is unbounded face out here. So this has 2 faces. The number of faces is closely related to the number of Jordan curves, like producing the thing there. Although it's not that easy. Like counting how many Jordan curves are given here is like has something to do with the number of cycles. Maybe it's like, but some don't necessarily produce a face, so you don't have to worry about that stuff now. Yeah. Anyway, so we can talk about faces. We can talk about unbounded faces, but keep in mind, and this is important, we can only talk about these objects in a planar embedding. If I give you a graph G and ask you about its faces, it doesn't mean anything until you've drawn it in the plane, right? Like just saying, how many faces does K4 have doesn't mean anything until I've actually drawn it. We'll discover later that the number of faces is actually fixed. If the graph is planar, no matter how you draw it, always has the same number of faces. That's maybe not totally obvious, but that's true. If the graph's not planar, you don't talk about faces at all, right? Because I mean, you could in principle, but we don't. Like if you have a drawing like this, say, like how many faces are here? Like this is, I mean, yeah, like if these, you could describe faces, right? You could, but you don't. Like this is not a planar embedding. I don't know if the inside here is 1 face or like 4 faces. It's not well defined, and you can redraw this in other ways too. Okay. So we only talk about if you have a planar embedding, so that's a drawing of G with no crossings, which is only possible for planar graphs. Okay, that's one definition. You can find more formal definitions of that in DSTL and so on, but we don't care. And then the other thing is a graph G is maximal planar, or a planar graph is maximal just if it's edge maximal. So it's planar, and if I add an edge to it, it becomes not planar. Okay, if G is planar, but addition of any edge makes it non-planar. Okay, and actually, like, or potentially you can't add any edge, right? Like K4 is maximal planar. Like there's no edge to even add, right? So the addition of any edge, of which there are none, makes it non-planar. I guess it's not really clear, but complete graphs will also, I mean, K4 and K3 are the only complete graphs, but so otherwise, if you have a planar graph and you can't add an edge to it, meaning any edge you add to it makes it non-planar, then that graph is called maximal planar, okay? Now, does this even make sense? Is this reasonable? Well, yes, if G is planar, you can draw it without crossing edges, and if you add edges to it, it's not clear whether the planar property is preserved or not, right? In general, it might not be preserved or it might be preserved, but you can remove edges safely, right? If I have a planar embedding, I can take away an edge and that won't destroy the planar property. Removing an edge doesn't magically introduce a crossing that wasn't there before, right? So we can definitely go down, and the question is, can we go up? Well, if there's an edge you can add and redraw it and be planar, then it's not maximal planar. But if every single edge you add somehow results in a graph that's no longer planar, then it's called maximal planar. I'm not claiming that checking that it's maximal planar is easy, right? You have to try to draw every single example of the graph with an edge added and confirm that it's not planar. But that doesn't matter, right? Like most mathematics, as a concept, it's well defined. It just may not be easy to establish the thing, okay? Here's one check, actually, okay, so in a maximal planar graph, so observe every face, and actually this requires a bit of topology, but I'm gonna gloss over it, will be a triangle, okay? In a max planar graph. Okay, and why is that? And even unbounded face. And so when I say triangle again here, I just mean bounded by 3 vertices here. It may not be a straight line triangle. And why is that? Let me prove this by example, essentially. So say I've got a face in my graph, and say this is the interior of the face and there's nothing inside of it, although there can be things inside in principle, and it's not a triangle, right? And so I've got my planar embedding and I see this thing here somewhere in my graph. Well, why can't I just add this edge here? It doesn't cause any problems, right? I added an edge, then I'm still not crossing, and I can even keep the same planar embedding and just add an edge here. And I can do the same thing here. I could add this edge as well. And now, like inside of here, I can't add any edges, but these are all triangles, right? Are there further edges I can add to this graph? Yeah, the unbounded face is also of length 5, and you can see this, I can actually add an edge between this one and this one here. I can't go through the interior, obviously, but if I go around here, I've added an edge. I still have a planar embedding. Curved lines don't matter. Now I've created a new face, but that's a triangle. That's good. I can still add edges though, because I can go here. Right? Still creates a triangle there. And now I believe I'm done. If you look at the unbounded face, it's now a triangle as well, right? It goes here, down to here, out to here. It is length 3 as well. And so this is actually maximal planar. If you'll examine it for a little bit, there's no edge that I can add here, okay? And so actually, these two are one and the same. Your maximal planar, if and only if, every one of your faces is a triangle. These two facts are equivalent to each other here, okay? It also means that if you're not maximal planar, you can produce a maximal planar without much difficulty. Just look for faces that are not triangles and add one of the edges or an edge until you get closer and closer and closer to being what we call triangulated, is what we often say there, okay? So that can be handy there. Actually, this concept already comes up in topology as well. Like this is a triangulation is a thing there. Okay. All right. So yeah, this is I'll say i.e. G can be triangulated. Okay, that's kind of why. And so occasionally we want to use that concept there. Okay, so we've got the big theorem here for today, which makes life much easier, that says if a graph is planar, there is an embedding where all the edges are straight line segments. So it's possible, right? This drawing here has curves, but you can always draw it with straight lines. There's a way to do it. That's highly topological, this type of idea here. And it's just handy that when you like want to illustrate or assume things, you can assume the line segments are straight. Somehow there's a way to do it, okay? Yeah, okay. So this is Ferry's theorem. Okay. So if G is planar, then there is a planar embedding of G such that each edge is a straight, that's redundant, but line segment. Okay, so there's some way to do it that we have no curves at all. So you can make these pictures nice. Okay. This will be handy for some theorems later. It's just a cool fact to know. It's often not proved in graph theory classes, but I think the proof is nice. There's one cool sort of extension of this, a conjecture that you'll notice there. It's an open question that can planar graphs be drawn with straight line segments such that all the line segments are of integer length? That's an open question in graph theory. We don't know if that's possible, right? Like, are there graphs? So any planar graph can be done with straight line segments. Is there a way to do it so that they're all of integer length? At first it seems reasonable, because if they were of like, you know, rational length, just blow the graph up, expand it so that all lengths become integral, like find a common denominator across all the lengths. But of course, I think you see immediately why that isn't solving our problem. What if I have a planar embedding drawing and some of the line segments are of length like √2 and pi and stuff like that? There's no way you're going to be able to expand that up to integer values, right? And so, like, it's open. We don't know how to do that. So the proof of the theorem here won't tell me the length of the line segments. anyway, so that's a really cool conjecture. Feels maybe more like topology than graph theory, but yeah, nonetheless. Okay, so let's prove Ferry's theorem that we can have a straight line embedding. That's sometimes we call it. Okay, so we're going to show a stronger statement. That's kind of similar. So the stronger statement we're going to prove is, given a planar embedding, there's a way to like shift the vertices around. Shift is in quotes. I don't define it clearly, but it's like the GeoGebra property where you take a point and you just move it and you let the lines and you're going to straighten out the lines too if you can. So there's a way to shift the vertices so that the line segments become straight, but also a vertex, the neighbors that it see come in the same sort of cyclic order around it, okay, as before. So we don't like wildly warp the graph. We kind of like, if we have a planar embedding, we can modify that specific planar embedding to get straight lines. Okay, so let me write this out. So given a planar embedding of G, we can shift vertices and straighten, whatever that means, edges. When we do the proof, this concept will become clearer. It's just hard to define it nicely. Such that each edge becomes a line segment, straight line segment, and for each vertex X, its neighbors, and I'll draw an example here, keep their clockwise, let's say, order around X. Okay, so let me explain here what I mean by this, especially by the second part here. So say here's X, and I started with a planar embedding. You know, here's its neighbors Y1, maybe Y2 was by a straight line segment, and Y3 also was curved here. All right, so say it was like this, and keep in mind, I mean, in this picture, you just say, oh, just straighten out those 3 lines and we're done, right? That's how you establish this picture, but maybe it's not that simple, right? Maybe there's a vertex inside here and here, and those are even like joined up by an edge somehow or something, right? So I have a lot of things to do simultaneously, right? There are multiple issues in this thing here. So like, I can't just straighten that out because it'll cross the red edge. So I have to move the red edge stuff too. So I'm doing all this simultaneously. But what it says is I can redraw this picture in the following way with X here, and then Y1, Y2, and Y3 like this. And when I say keep their same clockwise orientation, what I mean is like, this doesn't become Y2 and Y1 is down here. Like I don't shift them around. I'm allowed to do that, certainly, right? Like if I wanted to redraw this and Y2 somehow was over here instead and gave straight lines, like that's okay in terms of a planar embedding, but it's not okay in terms of the stronger statement I'm going to draw here, right? I'm going to prove it with the even stronger statement that I don't shift Y2 dramatically, okay? This seems to make things a lot harder, but like many induction proofs, it ends up making it much easier because we're going to preserve this property and it's going to be useful for us in the proof. Okay, so does that make sense, this operation? I'm going to straighten the lines, I'm going to get a planar embedding, and I'm also going to keep for every vertex, if I sort of walk clockwise around its circle, its neighbors are going to appear in the same order there, okay? And I can start with any planar embedding I want. It can be a really, really ugly one, but there's still some way to do it. Okay, so the first observation we can make is that without loss of generality, we can suppose G is maximal planar, right? If I can figure out a way to embed a maximal planar graph with straight line edges, then all of its subgraphs have been embedded with straight line edges as well, right? Very simple. This is handy. So now I have some nicer structure to my graph, but if there's a way to prove the theorem for a maximal planar graph, then I can prove it for any graph. Okay, and the proof will be by induction on the number of vertices of G. Okay, the base case is immediate. The base case is when n equals 3. When n equals 3, the maximal planar graph looks just like a triangle. There is a planar embedding of the triangle. Actually, be careful. We're proving a little bit stronger statement here But if you think about it for a little while, if I start with something that's a triangle and doesn't have curved edges, if I just, like, I can easily straighten those edges out, right? I mean, like, just keep the vertices where they were. I don't care what the edges look like. Just replace them with these 3 edges, and it'll, then I did my shifting. I didn't even have to move my vertices. My lines were straightened out immediately. And each vertex, its neighbors appear in the same order because they literally didn't move, right? The orientation of the neighbors in this clockwise order doesn't depend on the edges. It depends on where the yi's appear in space, right? So that's immediate. Okay, so now n is greater than 3, whoops. And assume the statement holds for smaller values, blah, 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 blah. Okay, so now we need to define a term, just temporary for this proof here. So a triangle, again, a triangle, we mean like 3 vertices with 3 edges, not necessarily a geometric triangle. In a planar embedding is what we call separating. Okay, this has nothing to do with connectivity. It's just defined for this thing here. If there's a vertex on the interior of the triangle and a vertex on the exterior in the planar embedding. Okay, so if there exists vertex X on interior of triangle and Y on exterior of triangle. Okay, so a triangle is separating if there's some vertex X on the inside here and some vertex Y on the outside there in the planar embedding. So somehow, like, this is not the what do you call it? Like the smallest, like this is not a face, okay, in a maximal embedding if it's separating, because this X here is a vertex, and since the graph's maximal, like there should be some edges inside of here. Like X should be on a triangle, and that triangle is like inside here. There may be additional vertices to X, but this is not like an innermost triangle, you might call it, of the graph here if it's separating. Okay. Why is the term separating? Separating just means that X and Y are separated from each other. There's no edge X, Y in the graph, right? That's clearly, because that would have to cross over. Okay. There may or may not be separating triangles, right? In our embedding of K4, this was a straight line embedding too, so we don't have to prove anything. But this guy here has no separating triangles. What am I saying here? What do I want? I want to get this right here. No, no, there's not. There is a triangle with a vertex inside of it, but there's no vertex outside of it, right? So yeah, it's not separating. You can have an X inside, but you need to have a Y outside to be separating. Okay, yeah. Okay, so now we need to choose an edge of the graph, and we're going to contract that edge and apply induction. So I need to pick an edge, and there's 2 cases. If there's no separating triangle, we can just grab any old edge. If there is a separating triangle, we have to be a little more delicate, okay? So if no separating triangle, choose any edge UV. Otherwise, if there is a separating triangle, choose edge UV such that U is on interior. Okay, I found a gap here in my presentation of the proof here. So I'm going to state what I think works here, but this may raise an issue that hopefully we'll resolve. We don't have a whole lot of time. I'll fix it in the notes though this afternoon. So U is on the interior of what we're going to call of an innermost separating triangle. What is an innermost separating triangle? That is a separating triangle that does not have a separating triangle inside of it. Okay, so let me give an example of one that's not an innermost separating triangle. Okay, so this triangle is separating because there's a vertex inside and outside, but say there's another triangle, potentially even using this vertex, with a vertex inside of it. This triangle is separating, but it's not innermost because there's a smaller triangle living inside of it that is separating that vertex and then any of the remaining 5 vertices. Okay, does that make sense? Does this exist? Yes, the graph is finite. We'll give you that this thing exists. If there are separating triangles, there are innermost ones. Not the innermost, but there do exist ones. Why? Well, if this one here is not innermost, then take this one. If that one's not innermost, it's not because there's a separating triangle inside of it. Just continue until it stops. It can't go forever, right? Okay, so no sep triangle inside. Okay. Now, that doesn't mean that there can't be vertices on the interior here, right? So let me illustrate here what this looks like. So we grabbed an edge UV such that U was on the interior of an innermost separating triangle. So here's our triangle, and here's U, okay? Now, there can be triangles inside of this region here, but if there are, there's no vertices inside of them, okay? So like, in fact, there even have to be triangles like on using vertex U. Like this is, I'm just drawing an example here. Like it could look something like this. There are many other ways it can look though. Like another way it can look is, and this is actually the one maybe it's worth working with. U might look like this, and then, yeah, by the way, there has to be a vertex out here, of course, as well. Otherwise, it's not separating at all. U might look like this here, and then this vertex could be V, say. In this picture, this vertex could be V, okay, etc. But there's no vertex inside of any of these triangles. And actually, there's additional things to notice here. Because this graph is maximal, like I can assume, again, this is just an example, this edge has to be here, right? Sorry, that edge has to be there. It can't go up there. Are we still safe here? I don't think we don't have a smaller separating triangle on the interior here. It's still okay, all right? All right, so I mean, these are just examples of how the picture can look. Okay, so now, as n is at least 4, we know that the edge UV, okay, U is on the interior of innermost separating triangle, is on boundary of 2 faces. An edge is always a boundary between 2 faces. Also, we're using that it's maximal here, okay? So an edge splits 2 sides, and the 2 faces are triangular. They both look like this. And let's call the neighbors X and Y here. And I'm going to put this as a claim, and this follows from the stuff above, but I have to gloss over this now. X and Y are the only common neighbors of X and, of U and V. Okay? Actually, maybe I can explain that real quick here. So U and V are the endpoints of these, and they have common neighbors X and Y, which form faces here. Suppose there's another vertex that's a common neighbor of both of them. Then we have this and this. And from here, we're going to find, although I don't see it immediately here, that this is going to violate the innermost separating triangle property here. Okay, you may not see it. I actually don't see it, so I'm gonna gloss over it for now because I want to finish this proof. But that's the fact that they only have 2 comes from this definition here. Something's a little fishy here, so I have to come back to it. Okay, so now let's look at, we have a planar embedding, okay? So we've got X, we've got U and we've got V. Is that what I want? No, I'm gonna draw it this way. So I'll finish the proof by picture. That's not what's in the notes, but that's the reason to do lecture here. So edge U and V, and I'm gonna be very careful here not to draw straight lines for these ones here, because it's a planar embedding. Like, I don't know if they're straight lines. I'm trying to establish straight lines here. And this picture, this thing may be a little bit unsatisfactory because it's a drawing, but let me try and make it clear as possible. X is here and Y is here, okay? Remember, these form faces, and this is the boundary between 2 faces. So like, this is sort of a prototype for this drawing here. It might look something like this. It could look a lot more complicated, right? This edge can go way off over here and come back around here. And then let me draw the remaining neighbors of U and V with a very specific labeling. So the remaining neighbors of U are A1, A2, A3, up to AK. And I don't care what these edges look like. I just care, these are their orientation in a clockwise manner in the plane here, right? A1, A2, A3, AK, X, V, Y. That's the orientation of the neighbors around U. If I can relabel U and V if U's on the left versus on the right, and I can rotate my planar embedding so that U is on the left and V is on the right. Like, certainly I can get U to the left of right of V if I want. And I can also get X and Y above and below if I want. And then V will have something similar. It's going to be labeled B1, B2, and then down to, let's make this one curved, B, say L. And so the orientation of vertices around V are X, B1, B2, down to BL, Y, U, right? And I mean, I can start the clock wherever I want, but those are the two orientations. Okay, so now with this picture here, I'm going to contract the edge UV. So contract UV. What happens when I contract UV? U and V become a new vertex, say W, that's adjacent to all of the AIs and BIs and X and Y. But I'm going to contract the planar embedding. So I'm going to pull those together and not like redraw the graph by magic, but I'm just keep the drawing that I have as best I can. So what's the easiest way to do that? If I have like an edge like this and it goes to U, and then I contract them to a new vertex W, just like follow the direction of the contraction. So this line, it happens to be straight, goes from U, and then it just extends like that. Does that make sense? Like that's the new segment. X went here. I can draw it straight down if I want, but let's just go down to here and then follow closely, right? We're using topology. Don't draw them on top of each other. Just bring them all together. So the new picture looks like this. I have W here, and then X is up here, Y is down here, and then I have all the previous neighbors. Again, these may not be straight lines. This was A1, A2, up to AK, and then B1 down to BL. That's my new drawing, and it remains planar, right? I contracted that edge, the drawing remains planar. By the way, X and Y are actually multi-edges, right? Because U and V were both adjacent to X and both adjacent to Y. I can actually, that's fine, right? Multi-edges are okay too. I just draw them like this, but I'm actually going to ignore them because the straight line embedding doesn't make sense when you have multi-edges. I mean, the planar embedding doesn't make sense. Planar embedding makes sense, but a straight line one wouldn't because they lay on top of each other. But I'll resolve that after. Okay, so I get this picture here once I contract the vertex. So all I want to emphasize is if I have a planar embedding here that looks like this locally and I contract UV, the resulting graph maintains its planar embedding, right? Don't move these vertices and just slightly shift their things to this vertex here. Don't affect anything else. This now relies very much on the fact that there's nothing inside of these triangles, okay? That's the innermost triangle property is very important here. If there's stuff inside of these, then contracting might cause crossings and stuff. But if there's a vertex inside of these triangles, then we would have chosen a different vertex for U, okay? All right, so let's like finish the proof here. We're basically done. I have a planar embedding. So there exists a planar embedding of G contract UV, right? It's here. I started with the original contracted, I have a planar embedding. This planar embedding doesn't necessarily have straight lines, but this planar embedding has fewer vertices than the original graph. So induction says, you can fix this guy to make its lines straight. So let me just say that. So, actually, these can be made straight, and what else? Not only can they be made straight, but I won't change the orientation around this vertex W. If I change the orientation and BL ended up over here and A5 ended up over here, that could happen, but induction says it doesn't. So all I do is straighten out everything I've got here, maybe moving vertices a little bit, but W sees these neighbors around here in the same place. And now all I do is just undo. Now I go back up here, keep all these straight line segments, pull W apart to U and V, just do it very, very tiny. Leave them epsilon close to each other, closer than any pair of vertices were in the graph. In fact, what I really care about, make them so close to each other that no other vertex is in there's a small ball around U for which there's no other vertex. Keep U and around W, sorry. Right, in this planar embedding, like there may be other vertices really close in here that have nothing to do with this, right? They may exist there, but certainly there's a small epsilon ball around W for which there's no vertices, right? I can always find an epsilon. So now replace that W with two vertices that are inside that ball. So they don't interact with these other vertices. And then all that happens is, so this now W, gets replaced with U and V on opposite sides really close. And now, for instance, these two edges here that should be was just one edge before, they're so close to each other to be negligible according to the other vertices in the graph. And moreover, this edge from AK to U that's here was basically identical to the W1. Like we can make that distance so small. Standard topology trick, right? So that it doesn't affect all the other stuff that we got by magic, by induction. And that's actually a planar embedding, okay? Now, it was crucial though, notice that I kept the ordering of the vertices on both sides, because again, if like B2 ended up over here, then how do I get V over to B2? Like I don't know, that crosses other things, but I kept the orientation crucially. And that's very much a magic trick, right? Induction allowed me to keep it, and I absolutely needed it, okay? And the real key was just to do this contraction trick somewhere interior enough so that there wasn't like stuff messing with me, okay? So a lot of it relied on a good definition of this, which I told you was a little bit hazy. I need to resolve it, but anyway, let's stop there.